Hey everyone, welcome back to Linear Algebra. This is going to be lecture 9 of the course. In this section we're going to discuss, we're going to shift gears a little bit and step away from linear systems for a moment. We'll be back to it in a bit, but we're going to go through a couple of lectures that are focused a little more on the internal structures that are present in matrices, and specifically we're going to talk about determinants and eigenvalues. So we're going to start with the determinant today, and this is a remarkable property of matrices. Many really important geometric and algebraic features or properties of the square matrix can be revealed by a single number that can be calculated from the matrix, and that number is called the determinant. And so we're going to go through what the determinant is, define it, do some examples. Okay. So we'll call this section 3.1, Introduction to Determinants. Okay. And so we're going to start by calculating determinants for matrices with smaller dimensions. So we're going to start with the determinants of 1 by 1, 2 by 2, and 3 by 3 matrices. Now what we'll discover is that calculation of the determinant the complexity of the calculation of the determinant grows exponentially as the dimension of the matrix increases. So we start naturally with these smaller dimension matrices, and also it works well to start with the smaller dimensions because it lends a little more real world grounding in what this number is and how to get to it. So we'll start with just the 1 by 1. So for a 1 by 1 matrix, right, we'll just say that's looks basically like that, just a single number. The determinant is basically the sole entry of the matrix. And so the determinant, denoted using this notation here typically, with the vertical bars, in this case is just equal to A11. Okay. So not very interesting. Let's jump to the 2 by 2 case. For a 2 by 2 matrix, in this case A will equal A11, A12, A21, A22, right? And so for this case we've actually seen the determinant before. We talked about it when we were discussing inverses of matrices previously. So in this case the determinant is equal to A11 times A22 minus A21 times A12, right? So remember, it's that multiply the diagonals process that we discussed previously with the matrix inverse. Okay, so an example here would be, let's just say A is equal to 4, -3, 2, 5. Okay, so if that's your matrix, then the determinant of A is going to be 4 times 5 minus 2 times -3. Right, so it's going to be 20 minus -6, so 26. Okay. So that's the case with the 2 by 2 matrix. So again, we've seen this one. The 1 by 1 is trivial, 2 by 2 we have seen. So let's jump to the 3 by 3 next and see how to calculate this magical determinant number in the case of a 3 by 3. So for a 3 by 3 matrix, right, now in this case A will be A11, A12, A13, and then A21, A22, A23, A31, A32, A33, right? So the 3 by 3 matrix looks like this. Now we'll talk a little bit more about how to think about this, but this matrix, this 3 by 3 matrix, has a determinant of A11, A22, A33 plus A12, A23, A31 plus A13, A21, A32, and then minus. All right, so this is, again, I'm just laying it out. We'll talk about where this comes from in a second. A13, A22, A31 minus A11, A23, A32, and then finally minus A12, A21, A33, right? So this is the 3 by 3 determinant. Now you can see, just going from up from a 2 by 2 to a 3 by 3, the complexity of the calculation grows very rapidly, right? So you can only imagine what the sort of brute force calculation for a 4 by 4 determinant would look like. It would be much, much larger yet. Okay, so this is kind of a terrible way to think about how to calculate the determinant by this, kind of brute force memorization. We're not going to rely on that at all. So, yeah, we will not be relying on memorization for calculating determinants. Okay, so instead we're going to talk through, for the 3 by 3 case, another way to kind of conceptualize the calculation of this determinant. Okay, and so what I'm going to do is I'm going to write out a matrix. So A11, A12, A13, A21, A22, A23, A31, A32, A33, right? So here's my 3 by 3 matrix that I just previously wrote out. I just wrote out all the entries in this grid. Now what I'm going to actually do is take the first column and the second column, and I'm going to add those on to the side here as well. Again, so A11, A12, A21, A22, A31, A32. Okay. All right, so I've got the matrix entries themselves, and then I've duplicated the first and second columns. And now, kind of the way to sort of remember the determinant calculation for a 3 by 3 is to remember this picture, which is easy enough to recall, and then think about multiplying these 3 numbers together, multiplying these 3 numbers together, and multiplying these 3 numbers together. Okay, so those 3 products will get you the 3 of the 6 entries in the linear sum that we just saw, right? So these 3, so you've got A31, A22, A13, multiply those together. A32, A23, A11, multiply those together. A33, A21, A12, multiply those together. Now the other 3 come from the opposite direction. Okay, so for example, this first one, A11 times A22 times A33, right? If we go back to the definition, that was actually the first combination. The second combination, A12, A23, A31, A12, A23, A31, that's this one. The third product is this guy, and then the last 3 are the other direction. So kind of the way to think about this, right? So obviously you can draw the picture. It's easy to remember this schematic. The arrows pointing to the right So the arrows pointing right indicate terms with a positive sign. Right, so that's these 3, right? So A11 times A22 times A33, that's a positive sign, positive sign, positive sign. Right, so everything with the arrow to the right is a positive sign. Everything with the arrow to the left, then, those are the negative signs. So the arrows pointing left indicate terms with a negative sign. Okay, and so this is a better way to remember it. Right? This is a better way to remember it. It's easy to remember this layout, right? I mean, it's just the matrix itself and then the first two columns duplicated, and then it's just arrows drawn in the natural places. Right? So the arrow has to include a product of three numbers, right? So it has to be diagonal, right? So here's the first one, the second one, the third one, fourth one, fifth one, sixth one. Right? So pretty easy to remember. Now, this technique is, sometimes called basket weaving, right? Because it kind of looks like how you weave a basket. This 3x3 method is called basket weaving. Mathematicians don't really call it that, but it's kind of an easy way to remember it because it uses this idea of basket weaving. So let's do an example with some real numbers and see if we can calculate this. So use basket weaving to calculate the determinant of, okay, and our matrix A will be 4, -2, 3, -1, 5, 0, and then 6, -1, -2. Okay, so this is our matrix, right? So no need to memorize anything, just remember the technique that we've just discussed. So we'll write out the matrix itself, the entries in the matrix, put them in this grid, and then let's duplicate over the first two columns. So 4, -1, 6, -2, 5, -1. Okay, and so we've got to multiply those three together. And so we'd have 4, 5, -2. Right, the determinant's going to be equal to those three, plus those three, plus those three. Okay, and so those are all the arrows in the right direction, and then the left direction are negative, so it would be those three. So 6 times 5 times 3 minus these three, 4 times 0 times -1 minus, and then finally those. So -2, -1, -2. Okay, and so again, we memorize nothing here, and we can remember how to do this. Okay, and so this is going to be, let's see, we got a -40 plus 0 plus 3 minus, now this is going to be a 90, minus, and then another 0, and then minus -4. Okay, and then when you add all of those up, you should get -130 plus 7, so -123. There we go. So there's the determinant of A. Right, so not terrible, not too bad. This may seem a little. This may seem like a strange way to think about a calculation, but it's a shorthand method of a more general method, which we'll discuss in a moment when we get kind of to the 4x4 case and above. But this is strange on the surface, but this reflects the general method that we'll use. Okay, all right. And so before we go further, let's talk about some kind of useful application, at least a useful application of determinants. So 2x2 and 3x3 determinants are sometimes interpreted as areas and volumes. Right, and we've actually seen this before. This was early on, maybe in the first section. Actually, no, you know what? I think this came up in Calculus 3, actually, now that I'm thinking of it, yes. This came up in Calculus 3 when we were talking about the cross product. And so the cross product, if you recall from Calculus 3, actually leverages the determinant in an interesting way. It uses something like the determinant. So let's talk through this use case here of representing areas and volumes using 2x2 and 3x3 determinants. Okay, and I should say respectively here. The 2x2 is interpreted as area, 3x3 as volume. Okay, so here's the theorem. Let's write it out. We'll write the theorem out for the 2x2 case, and then we'll just talk more generally about the 3x3 case. So let's let x be a vector, x1, x2, and y a vector, y1, y2. Okay, so let x and y be these vectors. So these will be two vectors that are non-parallel. I should put that, non-parallel, right? They can't be parallel, otherwise this doesn't work. So they're two vectors, non-parallel, in R2, naturally. And they need to begin at a common point. Okay, so beginning at a common point. And then let's draw a picture here just to make sure we kind of see what's going on. So I've got some vector here, which I'll call x, and then I got some other vector here, which I'll call y. Right now, if you think about, and they obviously start at a common point here. Now, these two vectors imply a parallelogram, right? So you can see a parallelogram implied here. And so what turns out to be the case is that the area of this parallelogram is given by the determinant of a matrix we can build off of x and y. So the area of the parallelogram is given by, and I'm going to write this slightly differently. I'm going to write the determinant of the matrix x1, x2, y1, y2, and it's actually the absolute value of that. Okay, so this is a slightly different notation. Actually, write the word det, determinant. Right, so I'll put down here, i.e., the absolute value of the matrix x1, x2, y1, y2. Okay, so that matrix. Very cool, right? So the parallelogram that is implied by these two vectors x and y can be, the area of that parallelogram can be found using the determinant. Okay, that's very cool. And this can be extended to the 3D case as follows. So for 3D, right, let x be a vector, x1, x2, x3, y be a vector, y1, y2, y3, and z a vector, z1, z2, z3. Okay, so those are the three vectors that are required for the three-dimensional space. So let's let these be vectors, not all in the same plane. Okay, and I should say, yeah, not all in the same plane is enough. So not all in the same plane, I was going to say non-parallel, but not all in the same plane means they're non-parallel as well. Then these three, let's draw a picture here. All right, so let's say I've got a vector going that direction, a vector going that direction, and then another vector going that direction. Well, these are going to imply, similar to the way that the previous 2x2 scenario implied a parallelogram, these are going to imply what's called a parallel parallelepiped, right? And so it's going to look a bit like this. Okay, and so you can kind of see, right? So you've got these corners here. Okay. So you can see this sort of parallelepiped, and it can be slanted. This one's a little more like a block, not so much, there's not, the angles all appear to be more like right angles here, but that's not necessarily the case, right? So this can be slanted down more if we want, but in this scenario, I just wanted to draw it nicely. And so what we can say here is that the volume of the parallelepiped determined by x, y, and z is given by, right, again, it's going to be the determinant, this time of a 3×3 matrix. So it's going to be the determinant of x1, x2, x3, y1, y2, y3, z1, z2, z3. So that's the determinant, and then we want the absolute value of the determinant. Okay, so that's two interesting applications. So you can get to the area of a parallelogram, thinking of this as the determinant, and you can get to the volume of a parallelepiped for 3 vectors, so defined and so arranged, using the determinant of the 3×3. Okay, and so this will come up later as we get further along in the course, but it's just an interesting application now, and I would encourage you guys to try to figure out how to prove this, right? And so start, of course, with the two-dimensional scenario. Start with this and think about what does the area formula for a parallelogram look like, and compare that to what the formula for this determinant looks like. And I think it's a very straightforward exercise. Then you can expand to this one using basically the same technique, same features, and you'll see that in fact it all kind of works out. Okay, fairly straightforward proof. But all right, excellent. So now what we want to do is we want to move further along and discuss determinants of higher dimensional matrices. So for determinants larger than 3×3, we'll need to introduce some new concepts. Okay, so let's go ahead and define, well, basically what we're going to need to define are two ideas. The first thing being the submatrix idea, and then the second item being what's called the minor, or the cofactor. Okay, so we'll start with the submatrix idea here. And so we're going to let A be an n×n matrix. Okay, and in this case, n needs to be greater than or equal to 2. Okay, and so given that matrix, the ij submatrix of A is going to be an n×n, n-1 by n-1 matrix. So is the n-1 by n-1 matrix obtained by deleting the ith row and jth column of A. Okay. Okay, so that's what we mean by the submatrix, the ij submatrix. Okay, and then a term that comes up here kind of connected to this is the idea of the minor. Okay, and so then the ij minor minor, denoted Aij, like so, is the determinant of the submatrix Aij. Okay, so this may seem like a lot of running around, but the actual definition for the determinant is going to involve these concepts. We just have to make sure that we know what they mean. Okay, it's actually relatively straightforward, right? So let's start with an example here. Okay, so let's say I'm given the matrix 5, -2, 1, 0, 4, -3, 2, -7, 6. All right, so I've got this 3 by 3 matrix. And we're just going to go 3 by 3 just because otherwise it's too much writing. It just takes too long. So if I want to write the A13 submatrix, what is that? Well, the A13 submatrix, think about the matrix itself in its entirety. So A13 is the submatrix obtained by deleting the first row and the third column. So you can kind of think of just like blocking those out, right? And so that means the A13 submatrix is 0, 4, 2, -7. Okay, what about the A23 submatrix? Well, in the same way, you can think about having the entire matrix A, but then blocking out the second row and the third column, so like these two. Okay, and what remains is the submatrix, so 5, -2, 2, and -7. Okay, what about A33? Well, I mean, eventually you want to be able to do this without having to rewrite the matrix each time, so you can just come in and imagine that column gone and that row gone, right? So the A33 submatrix is 5, -2, 0, 4. Again, just imagining those two out of the picture. Okay? And so that is what we mean by the submatrix. Now, what is the A13 minor? Well, that's just the determinant here, right? So it's the determinant of this matrix, right? And so we know this is a 2 by 2, and so the determinant is easy to calculate. It's just going to be 0 minus 8, right? And then the A23 minor is going to be the determinant of this, so 5, -2, 2, -7, and so that's going to be what? -35 minus -4, so that's -35 plus 4, so -31, right? And similarly, the A33 minor is going to be the determinant of this guy, right? So it's 20 minus 0. Okay, all right, so you've got the submatrix, you've got the minor, which is the determinant of the submatrix. Okay, and we just need one more item then, and we'll be ready. So we've got the submatrix, the minor, and now what we need is what's called the cofactor. Okay, so here's the last definition. Oops. The last definition. So again, we'll let A be an n by n matrix with n greater than or equal to 2. The Ij cofactor of A, right? And this is sometimes denoted as Aij, but it's usually like a script, like a cursive script if this is in text, and so you need to put some kind of an indication that this is a, kind of a more cursive Aij. That's a terrible way to write it. So let's say, however you want to do it, just so you know that this is not the submatrix, this is something different. This is the cofactor. All right. So the Ij cofactor of A, denoted with this cursive script, is going to be basically -1 raised to the I plus j power times the ij minor of A. Okay, so what does all this mean? All right, so what does this mean? Well, it means that aij, the cofactor, the ij cofactor of A, is equal to -1 raised to the I plus j power times the ij minor. Okay, so in sort of more standard terms, the ij cofactor is equal to -1 raised to the I plus j power times the determinant of the ij submatrix of A. Okay, so a little bit convoluted, but let's see an example. It's a fairly, I mean, it's a little cumbersome on the surface, but it's actually not too bad when we see this in practice. So let's take a look at this. So let's say I have a matrix A, and just like make it simple: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've got this 4x4 matrix. And let's say I'm interested in the 3, 4 cofactor. Right, so we just want to write that out. What is it? Well, so again, it's A34, right? Kind of this cursive script. It's just going to be equal to -1 to the 3 plus 4 power times the determinant of the 3, 4 submatrix. Okay. All right, so let's talk this through. What does this look like here? So I've got -1, and this is obviously the 7th power. And then this is going to be a submatrix A34, so that means third row out, 4th column, right? So you can kind of come in here and either do this in your head or do it explicitly. And this is going to be the matrix 1, 2, 3, 5, 6, 7, 13, 14, 15. Okay. And so this is going to be the A34 cofactor. What about the A12 cofactor? Well, that's -1 to the 1 plus 2 power times the determinant of the 1, 2 submatrix. So that's -1 to the 3rd power. And then here we're going to cross out the 1st row and the 2nd column. Okay, so I've got 5, 7, 8, 9, 11, 12, and then 13, 15, 16. Okay, and then so these are 3x3s, right? So you can calculate those determinants using the basket weaving approach if you like. I'm not doing it just in the interest of time, but the focus here is just the structure, you know, of these cofactors, how they're structured, and kind of extracting them from a matrix. You know, not actually calculating the 3x3. That was 25 minutes ago. Now we're on to something else here. So that's the idea. That's the idea here. And so, given this, you can kind of, well, let's actually define the determinant, and then we'll talk about it. You know, some of the issues that arise with it. So the determinant can be defined in terms of these cofactors, minors, and submatrices. And here's kind of the best definition, the most general definition. This works for any n by n matrix, no limit on the dimension. So we'll let A be an n by n matrix, n by n matrix. Okay, I want to make sure that's clear that says n by n. There we go, n by n matrix. Then the determinant of A is, right, so there's two cases. if n is equal to 1, then the determinant of A is just equal to the lone entry of A. If n is greater than 1, then the determinant of A is equal to, there's different ways to write it. I'm going to start by writing it this way. So an1 times A, and this is the script A, plus an2 times an2 plus an3. Oh, shoot. I'm sorry. So an1 times the n1 cofactor plus an2 times the n2 cofactor plus, and then I want to really do a dot 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 here. And then finally ann times the ann cofactor. Okay, so that's the definition of the determinant for any matrix, for any n by n matrix, right? So obviously the 1 by 1 and then 2 by 2 and above is captured by this. Okay. And so what is this an1? Well, that's just the n1 entry of the matrix, the n2 entry of the matrix, and the nn entry of the matrix, right? So in the case of a 3 by 3, it would be, you know, the 3-1 entry would be 13, the 3-2 entry would be 15, the 3-3 entry would be 16, right? So this would be 13, 15, and 16. And then what is this an1 script, this like cursive script an1? That is the minor, right? The determinant of, or sorry, that's the cofactor expansion. Yeah, sorry about that. Right, so note that a n I is equal to -1 to the n plus I times the determinant of the a n I submatrix. Okay. Okay. All right. Let's do an example. I'm going to rewrite the definition here, or at least the n greater than 1 portion of the definition, just for reference here. So for n greater than 1, the determinant of A is equal to an1 times an1 plus an2 times an2 plus dot 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 plus ann times ann. Okay, and so these are entries, these are cofactors. Okay, and now recall, very important, ani is equal to -1 n plus I power times the determinant of the ni submatrix. Okay, right? All right, so let's do a concrete example here using this definition. Okay, so let's do an actual example. So find the determinant of, and then I'm just going to do a 3 by 3. We'll do a 4 by 4 today, but I want to start with this one, just a little smaller. So 5, -2, 1, 0, 4, -3, 2, -7, and 6. Okay, so this is our matrix A. All right, so let's write out the formula here. All right, so this is a 3 by 3, so n is equal to 3. And so the determinant is A31 times A31 plus A32 times A32 plus A33 times A33. All right, so that's easy enough. And let's write it out in more detail. Let's go down to the next level. So the 3-1 entry here is 2. Okay, And then this is, remember, the cofactor, so you have to have -1 to the 3 plus 1 power times the determinant of the 3, 1 submatrix. So cancel out the third row, first column. So -2, 1, 4, -3. Okay, that's this one. That's this one. Plus, and then A32 is -7, and then times -1 to the 3 plus 2 power. Okay, and then that submatrix is going to be, let's see, it's going to be 5, 1, 0, -3. Okay, and then plus the A33 entry, which is 6, times -1 to the 3 plus 3 power. And then that submatrix will be 5, -2, 0, 4. Okay, so there we go. Okay, so that's the setup. All right, so this part here again is the entry, and then this part here is the cofactor. All right, just to make plain what's going on here. So that's this guy, and then this one here is that cofactor. Okay, and we can go through and obviously calculate all of this. So I've got a 2, and then that's -1 to the 4th power, so it's just 1. And then this determinant here is going to be 6 minus 4. Okay, plus, and then I've got a -7, and then that's going to be a -1 here. And then this is going to be -15 minus 0. Okay, and then I've got a 6 times 1 times 20 minus 0. Okay, and so that is the, and then we can just combine everything here. So this would be a 4, and then here I've got what is this? So -7 times 15, that's going to be 105, yep. 7 times 5 is 35, plus 7 plus 3 is 10, yep. So that'll be actually a -105. And then this over here, this is 6 times 2 is 12, 120, so plus 120. And so that means I've got 15 plus 4 is 19. Okay, so the determinant of this matrix is 19. And now you could go back and recalculate this using the basket weaving technique, because this is a 3 by 3 matrix, and you could just confirm this. All right, you can just confirm this. Excellent. So that's kind of that's a basic approach to calculating. I mean, this is the most general approach to calculating a determinant. Right now, I guess I misspeak there a little bit, because in general, like, the choice of using a cofactor expansion along the nth row, notice how the definition uses the cofactor expansion along the nth row, right? So the row is always fixed as row n. So in our example here, we had row 3. We took all of the entries of row 3 and multiplied them by the respective cofactors. That choice is sort of, I mean, so it's advantageous to start by using just the nth row as your cofactor expansion row. But in general, that's not, there is a more general definition that says you can do a cofactor expansion along any row. Right, so let's see an example of that. Let's actually do this same, keep with the same matrix in mind. Let's try to calculate the determinant by doing a cofactor expansion across the first row instead of the last row. You could do it equally using the second row. But let's do it with across the first row. All right, so let's write it out. That would be A11 times script A11 plus A12 times script A12 plus A13 times script A13. Okay, and so we can write all of that out. So the 1,3 entry is 5, and then it's a -2, and then it's 1, right? So I'm just going to grab those 3 and bring them down here. So I know this is 5, negative 1, and then this is 3. So I said 1. Sorry, that's negative 2 and 1. 5, negative 2, 1. Okay, 5, negative 2, 1. Okay, so I've got 5 times negative 1 to the 1 plus 1 power times the submatrix, which would be 4, negative 3, negative 7, 6. Plus negative 2 times negative 1 to the 1 plus 2 power times the submatrix 0, negative 3, 2, 6, plus 1 times negative 1 to the 1 plus 3 power times the 1, 3 submatrix determinant, which is 0, 4, 2, negative 7. All right, so we've got this guy. And this would be 5 times 1, and then this is going to be 24 minus 21 plus negative 2 times negative 1 times 0 minus negative 6 plus 1 times 1 times 0 minus 8. All right, and so what do we get here? We get 5 times 3, so that's 15. That's 5, that's a 3. 5 times 3 is 15. And then this is negative 2 times negative 6, and so that's 18. Or sorry, 12. Plus 12. And then this over here is just negative 8. Okay, and so 12, you can say 12 minus 8 is 4, and 4 plus 15 is 19. Right, so again, you can see you get the same answer. So the expansion can actually be done across any of the rows. It doesn't have to be the last row. I think it makes sense to think of it as the last row, at least when you're starting out, because then, you know, it kind of counts up, you know, so it goes from A31, A32, A33, right? So it's kind of easier to remember that way, but it doesn't have to be done that way. Okay, so let's let's see what's involved in calculating a 4x4 determinant. Okay. So calculate the determinant of, and say A is equal to this guy, 3205, 413, negative 1, 2, negative 136, and 502, negative 1. Okay, so it looks a bit like that. So there's our matrix A. So again, we're going to use the cofactor expansion along the 4th row. Okay, so the definition, excuse me, the definition is the determinant of A equals A41 times script A41 plus A42 times script A42 plus A43 times script A43 plus A44 times a script A44, cofactor A44. All right, and so we can write this out. A41 is the number 5, and then times negative 1 to the 4 plus 1 power, which is the 5th power, and then times the submatrix that you get by deleting the 4th row in the 1st column, right? So you have to imagine this row gone and this column gone. And so it's basically this 3 by 3 up here, isn't it? 2, 0, 5, 1, 3, negative 1, negative 1, 3, 6. Right, so that's the first term. The second term, A42, is actually 0. So that means the whole thing will be 0, right? 0 times anything is 0. So nicely we can just put a 0 there. The third term, A43, is going to be 2. And then it's times negative 1. And then it's to the 4 plus 3 power. So that's going to be the 7th power. Okay, and then the cofactor, or sorry, the minor here is going to be obtained by finding the determinant of the 4, 3 submatrix. So delete the 4th row, 3rd column. Right? And when you do that, you get 3, 2, 5, 4, 1, negative 1, 2, negative 1, 6. Okay, and then finally the last one, A44, is negative 1, and then it's negative 1 to the 8th power, 4 plus 4. And in here you're deleting these two, right? And so 3, 2, 0, 4, 1, 3, 2, negative 1, 3. Okay, right, so that's what the calculation looks like. Now notice here that in this formula for the determinant, you actually have 3 by 3 matrices, right? So your cofactor involves the determinant of a 3 by 3 matrix. And so you have to find each of these sort of separately. Now it is possible to do a further expansion here to actually write it out, right? i.e. to, expand this using the definition. But at this point, it might be faster to use kind of the basket weaving method. But let's talk about how this expansion would look, what it would look like, right? So here I'm specifically interested in this guy. So this is the determinant of A41. So let's see what that looks like. Okay, when I do that, so I'm again just going to apply the definition. Right, I'm going to apply the definition, but this time it's going to be applied to a 3 by 3 matrix. Right, so I'm just going to go through this kind of quickly. So it'd be negative 1 times negative 1 to the 3 plus 1 power. That's this guy. And then the matrix is 0, 5, 3, negative 1. And then plus 3 times negative 1 to the 3 plus 2 power, so the 5th power, times the submatrix 2, 1, 5, negative 1. Okay. Plus 6 times negative 1 to the 3 plus 3 power, which is 6. Right, and then 2, 0, 1, 3. Right, and now this we can calculate. Right, so I'm going to get what? Negative 1 times 1, and then this determinant is 0 minus 15. Plus, and then it's 3 times negative 1, and then this is negative 2 minus 5, plus 6 times 1, and then it's 6 minus 0. All right, and so finally, what do we get? 15 plus 21. So this should, yeah, negative 3. So plus 21, and then this is 36. Okay, and so for this 3 by 3, this particular, all we're doing is looking at this one so far. We've got to do the same thing for these. But for this one, this A41, we can see that the determinant is 72. Okay, now what about these two? Well, you'd have to figure it out the same way, right? You'd have to go through, calculate the determinant for each of these. And so this guy here, I've done this ahead of time. This is negative 67, and this one turns out to be 6. Okay, and this one we just found was 72. But you go through and do the same process. Right, and so that means the determinant of A is equal to 5 times negative 1 times 72 plus 0 plus 2 times negative 1 times negative 67 plus negative 1 times 1 times 6. All right, and so you can go through and figure this all out. And so what is this? 72 times 5, that's 10. So that's 360 negative. Plus 0 plus, now what is this? 67 times 2 is 134. And so this is plus 134. And then this one over here is negative 6. Okay, and you can figure out what this is. Looks like it's negative 232. Okay. All right. And so that's an example of calculating a 4x4 determinant. So a very, very, very difficult thing to calculate for matrices, by hand anyways, for matrices larger than 3x3. So the 4x4 is doable. 5x5 becomes unbearable practically. And I tried a 5x5 once, and I was like, I'm never going to do that again. But it follows the same process. It's just that the submatrices have to be calculated, and then the submatrix has to be calculated. So it just becomes a very involved calculation. Now, a computer can do it in a fly, but a human takes a lot of practice. Right? So that is the idea. That is the idea of how to do this. And so an n by n matrix will actually have how many cofactors? It'll actually have n squared cofactors. That's part of the reason that this is so convoluted, right? So an n by n matrix will have n squared cofactors, right? So 2 by 2 has 2 squared equals 4. A 3 by 3 has 3 squared equals 9. A 4 by 4, 4 squared equals 16, right? And so you can see it ramps up really fast. So excellent. Okay. Perfect. So I think that's where we'll leave off for this section. And when we come back next time, we'll talk about we'll talk more about determinants, and we'll see how the determinant is connected to row reduction and row operations generally, right? And then following that, we'll get into eigenvalues. What the heck is an eigenvalue? All right. So that's where we'll leave it, and we'll talk to you all next time. Take care.